Cool. Hi, everyone. How's it going? It's 11:05 right now, so it's time to start our Data 101 workshop. So hope you guys have had a great day so far. We are going to begin recording. So my name is Will, and I'm currently one of the education co-directors for this year for DataSoc. And I would like to introduce you to my other co-director, Matthew.
Yep. Hey, I'm Matt. I'm the other co-director for this year.
Cool. So we know that Data 1001 is an introductory course to data science at UNSW. So for all the first years and for all the people who are taking this course, this is a great summarization of the lectures and the slides and the tutorials of the course. So I would also like to thank my subcom, Aria, Meet, Jocelyn, and Faris for the contribution to this workshop as well. So let's get on to the next slide. So this is the agenda of today. We'll be starting off with the structure similar to the lectures and the tutorials. We'll be going through each topic step by step, statistics, computer science, and business, with a photo in between as well. So yeah, if you guys saw the attendance form, please make sure to fill it out as well. And if everything's cool, I'll hand it off to you, Matthew, for the statistics part.
Yep, no worries. Okay, so to start off today's workshop, we'll be looking at statistics. So statistics, I think in general, is just a collection and analysis of data to hopefully identify any of the underlying insights within that data, and therefore to extrapolate some kind of value from that. So in terms of statistics, you'll look at things such as set operations, probabilities, variables, and random variables. And those aspects of stats will be what we kind of cover in today's lesson. Right, so to start off with, let's look at set operations. So with sets are simply the collections of certain values that all belong in a certain collection. So an example of a set would be everyone in DataSoc, or it might be everyone in UNSW, for instance. And with sets, you can have different combinations of sets, you can have different interactions. And with these combinations or operations, we can also find the resulting probabilities. And that's what we'll be kind of covering today. So firstly, let's start off with negations or complements. So in terms of that, if we think about the complement of a set A, then that's just looking at all the values that aren't in that particular collection. So in this situation, where set A is that white circle as represented in the Venn diagram to the left, then everything outside of that, so highlighted in green, is just a complement of that. And in terms of probability, that's just 1 minus the probability of everything in set A. Now, next, we'll be talking about intersections. So intersections, if we think about two sets, so set A and set B, then any intersection is all the values which belong in both sets at the same time. And how we represent that on a Venn diagram is just anything that's in the physical intersection between the two spaces, as you see there. Now, related to intersections, we also have unions. So unions, instead of thinking about something being in both sets at the same time, a union describes a situation where you're in either set A or in set B. So that could constitute either you're only in set A or only in set B, or you could be in both sets at the same time. And using that kind of intuition, you can also have the resulting formula, which is known as a union rule. So that's the probability of set A plus B less the intersection gives you the union between the two sets. Now you also have something known as independence. So independence defines, well, if a value is known to be in set A, then you know that sets B and sets A are independent, so they have no information between the two. If the probability of being in set B is not influenced by being in set A. So that means that the conditional probability of being in set B is not influenced by that of set A. And finally, you also have mutual exclusivity. So that means that the intersection between two sets, so set A and set B, just is like the null set, the zero set, because there are no intersections in between. So that kind of concludes what set operations is about. And very related to this, you also have probability fundamentals. So this just describes the different formulas and probabilities you'll have and how you kind of relate, well, certain formulas like, well, the joint probability formulas, the marginal and conditional probability formulas. And this gives you a relationship between the two. So these are some pretty useful relationships to have. So to start off with, let's look at an example that illustrates how probability fundamentals operates. So in this situation, let's look at the left-hand side, where you have about 100 different individuals within a cohort. Now, with that cohort, you have two main descriptors. So that is the gender of a certain individual. So that could be either female or male. And you also have a descriptor which describes their opinion on what a dress color is. So the dress could either be blue or black, so BB, or it could be either WG, so white and gold. And I think that's like a reference to some internet meme in a few years back. But so in this question, so question one, what is the probability of someone being both male and also believing that the dress was black or blue? So in terms of how I would describe that, that's just being in either set M and set B at the same time. So I might give you maybe 10 seconds to try and do that for yourselves. And yeah, hopefully just put your answers in the chat in terms of what you think it is. Okay, so I think we're starting to get some answers. Oh, okay, so sorry. So will the recording be available later? Yes, it will be. It will be posted via a link. But hopefully that was enough time to go through that question. So this is I think, a pretty intuitive question in that in this case, you're looking at the probability of a value being in the intersections between sets M, so male, or the intersection between set B, so BB, right? So this is given by X divided by 100, where X is the total amount of people who are both in sets M and sets BB. Now we don't actually know the value for set X, so sorry, value X. So therefore, in the second line, we can establish a relationship, which is X plus 10 is equal to 49. Now, how we get that relationship is we look at the second column, so all the people who are male, and we know in total, there are 49 males, of which X people are in set BB and 10 people are in set WG. So therefore, using that equation, we can find that X is equal to 39. And as such, the intersection, or the probability of a value being in the intersection between two sets is just 39%. So that is answer C. Now, in the second question, let's find the probability that a person is female. So in this question, we'll be using the marginal probability formula. So that's in the second line in the, I think, the left-hand side where you have all those formulas there. So in this question, to find the probability that someone is female, you simply look at all the different probabilities of a person being female intersecting with all the other sets. So in this case, all the other sets are either sets BB or WG, and therefore the intersections correspond to values 32 and 19 respectively. And you also get those values just from that first column where you have 51 people in total. As such, adding up those probabilities together, you get a total probability of 51%. So that is the probability that a person is female. That's answer C. Okay, so moving on from the basics of probability, you also have something known as Bayes' theorem and diagnostic testing. So previously, we would have briefly touched upon conditional probability in that we look at the probability of someone in, say, set B, given that you know that the value is already in set A, right? And usually to find that probability, we would just use the intersections between set A and B and use that as a numerator. However, what Bayes' theorem does is it allows you to create a relationship in between the conditional probability of being in set A given B, and as well as its inverse, so B given A. Now, an example of this is illustrated here. So in question 3, an oil exploration company currently has 2 active projects, so one in Asia and the other in Europe. Now let A be the event where an Asian project is successful and B be the event where the European is successful. Now suppose here that A and B are independent events with the probability of A being 0.4 and the probability of B being 0.7. And I think in probability terms, this is just 40% and 70%. So as such, given that at least one of the two projects is successful, what is the probability that only one of the only project A, so the Asian project, is successful? And out of all the possible answers, you have answers A to D. And in terms of the formula you can use, I think the useful formula would be Bayes' theorem, so as given on the right. Now, I would also like to preface that in this question, when it asks for at least one of the two projects being successful, this is equivalent to asking the probability of observing the union between sets A and B. So project A or B being successful. So I might give you maybe 30 seconds to try and calculate that for yourself. Okay, so hopefully that was enough time. Now I'll basically be going through how you apply Bayes' theorem in this particular context. So in this question, looking at the first dot point, we have all our information. So that is the probability of being in set A is 0.4, whereas the probability of being in set B is 0.7. Now, what we want in this context is the probability of being in set A, so the Asian project is successful, given that the union of A and B is true. So that is either one of the two projects is successful. So using Bayes' theorem, we can re-represent that probability using this formula as given. So that is the probability of the union between the two sets given A times by the probability of A divided by the union. Now, in this question, we can immediately find what is the probability of A or B being true, given that A is true, because this is just 100%. And that's because you know that since A is true, therefore either A or B is true. Now, secondly, we can also find the probability of the union of the two events. And that is, we take the probability of A plus B minus the intersection between the two events. And that's just from applying the union rule. Now, in terms of finding the intersection, because we know that the two projects are independent, we can just take this as the product of the two respective probabilities. So therefore, we know that the probability is 0.82. And therefore, substituting in our unknowns, we find that the probability is just 20 over 41. Okay, now that we know what Bayes' theorem is, using this in actual, applied ways, we can actually use this in diagnostic testing. So that is, in a real world situation, suppose someone has like a disease, for instance, and we have some way to test whether the person is positive for that disease, or we can test if they don't have the disease. Now, it's quite useful in these real world situations to find the conditional probabilities related to testing. So that is, if we want to test for a positive result, then we might be interested in testing for a positive result, given that the person has a disease. So therefore, you can see that Bayes' theorem becomes quite relevant in these particular situations. And that's illustrated in question 4. So in this situation, you have the respective probabilities for certain conditional probabilities. And in this question, you want to find what is the probability that someone has a disease, given that the test came back positive. So in this question, it will be quite useful to use Bayes' theorem as shown there. And how we find that is, firstly, let's define two events. So one is D as someone is test positive, or someone has a disease, and T being someone gets a positive result for that particular disease. Now the info we're given is T given D, so that is 0.9. And the second point is that we test negative for a disease, given that someone doesn't have the disease, and that's 90%. And we also have the probability that someone has a disease as 1%. Now what we want is, what is the probability that someone has a disease, given that they've tested positive. And we can use Bayes' theorem in this context to try and calculate that. Now, for that expression on the numerator, we actually have those two values. However, we don't actually have the denominator. So what is the probability of testing positive for that disease? So under our note, we find that the probability of testing positive is given by our joint probability formula. So that is, we add up all the different intersections between testing positive for the disease, as well as all the other sets that a person can be in. And since we don't directly have that, we have to use the conditional probabilities we're given to try and solve for those intersections. Now, in this situation, we also have to use the complement probability because for our second term, so probability of T given DC, we actually don't have that value. So we have to use the complement probability to try and find that. And solving for that particular value, we find that the probability of testing positive is 10.8%. Therefore, substituting in our unknowns, we find that the probability of having a disease given we tested positive is 1/12. Okay, so moving on from looking at Bayes' theorem, set operations, and probabilities, in data science, you'll also be presented with different kinds of data. And with those data, they're not always in the same format. So there might be quantitative variables and there might be qualitative variables. So the main difference between the two is they're either numeric variables. So you can think about those as, say, integers. And you can also have qualitative variables. So that could be the classes that something will be in. Now, under qualitative variables, you can have these separated by a sense of order. So they can be ordered, so ordinal, or they can be nominal, so unordered. Now, in quantitative variables, you can also have countable variables. So those are discrete. And you can also have measurable variables, so continual. Now, in terms of variables, while you could have deterministic variables, so these have a set value, so say x is equal to 2, you might also be in situations where you don't actually know the outcome of a particular variable. So you don't know whether x is equal to 2 or it could be 3, 4, any value. And as such, in this case, it's known as a random variable. So a random variable does not have a particularly set value, and instead it could equal a certain range of different values where where it has a distribution over those particular values. So it has particular probabilities of taking on certain values. And random variables can either be discrete, so countable, and they can either be continuous, which is taking on any value within an interval. Now, the main difference between discrete and continuous values is, well, under discrete values, if you ever want to find some kind of value, you'll usually be taking the summation of that, whereas under a continuous random variable, you'll be usually integrating. And apart from that, you also have some summary statistics, such as the expectation, as well as the variance of those variables. So moving on to specific kinds of random variables, we can start off with a very special case of a discrete random variable, and that is the binomial distribution. So a binomial distribution in terms of a random variable is set out with two parameters. So that is n and p. Now you can intuitively think of a binomial random variable as, say, if you have n trials of some independent events. So each individual trial either has two possible outcomes. So one is a success or one is a failure. And in total, well, you'll have a particular probability of observing a success in each trial. And that's what your P defines. So the probability of having a success. Now, in a binomial distribution, it's also important to note that these trials are independent. And from there, you can also find the mean of a binomial distribution. So that's just NP. And the variance is given by its mean times by the complement probability, so the probability of failure. And you're also given that the PMF, so the probability mass function, is given as shown below. Okay, so in terms of the binomial distribution, we'll show a quick question which shows you how to actually apply the PMF. So in this situation, you have a restaurant where on average, if we define an outcome as successful if someone asks for water with their meal, then we know that on average, 3 out of 5 customers ask for water with their meal. So that is, there's a 60% probability of success. Now, in this question, you have a random sample of 10 customers who are selected. So that is, you have 10 trials of some independent event. Now here, you want to find the probability that question 1, so exactly 6 people ask for water with their meal, and question 2, which is less than 9 people ask for water. So with this question, in part I, it's fairly intuitive in that all you need to do is you need to take the PMF, so the probability mass function, and you just substitute in your parameters. So 10 is your number of trials, and 3/5 being your probability of success. And as such, the probability of observing 6 people asking for water is just 0.25. Now in part 2, this asks for the probability that x is less than or equal, is less than 9. And to find this, you could just substitute in the PMF with all the values from 0 to 8. However, that can be quite cumbersome in that there are 9 possible values you need to test. And as such, we can kind of create a shortcut in that we just find the complement probability. So we use the probability that x is greater than or equal to 9. And as such, we only need to substitute in 2 values, so 9 and 10. And substituting in those values, we find that the probability that less than 9 people ask for water is 95%. Now, apart from finding the probability of the binomial distribution and certain cases of that, we can also find the summary statistics related to the binomial distribution. So that is, what's the mean, variance, and standard deviation of a binomial variable. So in this question, consider the case where you're selecting 3 people at random for a committee. So this just tells you that there are probably 3 trials in total, where in this case, each person is independently selected, and there's a 50% chance of them being female. And in this case, let X be the number of people who are female on the committee. So what are the summary statistics for variable X? Now, it's useful to note that our random variable X is a binomial random variable because its sample size and probability of success is fixed. And you also know that there's a binary outcome and that the independent condition is null. Now, to find the mean first, we can use our formula for the mean, and that is just n, so your number of trials, times by p, so your probability of success. Now, in this case, we know that there are 3 people selected in total, so that's just 3 as our number of trials. And we know that the probability of selecting a female is 0.5, so that's your probability of success. As such, substituting in your parameters, that just gives you 1.5, and that's just equal to your mean. Now, to find your variance, you can just take your mean and you can multiply that by the probability of failure. So that's just 1 minus 0.5. And using that probability, we can find that the variance is 0.75. And finally, to find the standard deviation, all we need to do is take the square root of the variance because that's just how it's defined. And therefore, we get that our variance is equal to the square root of 3 over 2. Now, in terms of other discrete random variables, you can also have something that's known as the Poisson distribution. And how I like to think about the Poisson distribution is it's almost like a binomial distribution. However, instead of being limited to total values from 0 to n, so that's your possible values, a Poisson distribution has a range that goes from 0 all the way to infinity. So it's almost like in terms of its possible outputs, that's just all the natural numbers. Now, in terms of this, you also have a few caveats. So one is that you assume that independent events occur over time. And you can also use, in terms of the Poisson distribution, this can be used to model count data. So for instance, if you want to define something as the count of times an event occurs in a given time period, this can be modeled by a Poisson random variable. So I think a particular instance of that is, let's say you want to calculate the total amount of cars that cross the Sydney Harbour Bridge in an hour, then you can use a Poisson random variable to calculate that. Now, the only parameter with a Poisson variable is lambda. So lambda just tells you the mean of the total amount of, the lambda defines the total rate at which your count or your events occur in a given time period. And using your lambda parameter, you can define the mean and the mean and the variance as lambda. And you also find that the PMF is given as shown there. And if you actually did want to use this in a question, the applications are very similar to the Poisson distribution. So just substitute into the PMF, and you can also use the complement probability if you want to find the probability of being less than or equal to a value. Now, moving on to continuous distributions, you also have the normal distribution. So in this case, the normal distribution is given by parameters mu and sigma squared, where mu defines the mean of the distribution or where the distribution is centered, and the standard deviation is given by sigma squared, so how spread out your distribution is. And the normal distribution is quite useful in that it's symmetric, so it has quite a lot of symmetry, and it's also unimodal in that it has one peak. Now, using the normal distribution, we also have a very important result, which is the central limit theorem. So that just states that if you take the sample mean of, say, n random variables, what happens is that sample mean will approach a normal distribution when you sort of add on more and more individual random variables, right? So that's quite a powerful result because your underlying random variables don't even need to be normal. They could be, say, gamma distributed or Poisson distributed, and they'll always approach a normal distribution. Now, there are a few caveats to the central limit theorem. In that one, it assumes that you have independent and identically distributed variables. So that is that, say, you're adding up x1 to xn, then all of these have to be, say, binomial distributed, or they have to be gamma distributed. They all have to have the same distribution, essentially. And they also have to have a finite mean and variance. So they can't just blow up over time in terms of if you were to plot them on a histogram. Now, the central limit theorem has some pretty important applications in that it can be used in confidence intervals. So say you want to estimate the mean of a population, so you just take the sample mean. Then in terms of finding the probability of the sample mean lying in a certain interval, so that could be like a 95% interval, then you can use the central limit theorem. So you can approximate that using a normal distribution. And so that's quite useful in that case. And you can also use some approximation. So say you want to find the probability the sample mean is less than some threshold, then you can use the central limit theorem and use a normal distribution to approximate. Okay, so that takes us to the end of the statistics section. And now I'll probably pass it on to Jocelyn to take you through the computer science section.
All right, thank you, Matthew, for the awesome presentation. We'll be going into computer science. Yeah, all right, so first we will be talking about binary search trees. So a binary search tree is basically just a data structure used for organizing and searching data where each node has at most 2 children. So the left child and the right child. So the value of each node in the left subtree should be less than or equal to the value of the current node, and the values of the right subtree should be greater than or equals to the value of the current node. So we have 3 components, which is the main top level node, and then we also have the left subtree and the right subtree. So the parent node refers to a node that has 1 or more child nodes. So in a tree, nodes are connected in a hierarchical manner where each node except the root node has a parent node and 0 or more child nodes. And the child node refers to a node that is directly connected to another node, known as its parent node. So in this example, 12 is the parent node of 9 and 21, and 21 is the child node of 12. And similarly for this, 5 is the parent node of 12, and 12 is the child node of 5. And next, we have leaf nodes. So what leaf node is it's a node in a tree, data structure that does not have any children. So it is the endpoints of the branches in a tree. All right, so we have the operation of searching. So basically, if the value is less than the node's the current node's value, you go to the left, while if the value is more than the node's value, you go to the right. So we begin at the root node, which is 5. And then, for example, we want to find 19. So 19 is bigger than 5. So we go to the right. And then 19 is bigger than 12. So we go to the right again. And then we can see that 19 is less than 21. So we go to the left. And then we get 19. Next, we have the operation of inserting, which is similar to searching. So basically, we want to insert 4. And since 4 is less than 5, we go to the left. And then since 2 is more than 4, 4 is more than 2, we go to the right. And since 4 is more than 3, we go to the right again. And then we just insert a node containing 4 on the right. All right, next we have removing. So there are three cases that we need to consider is when the node we want to delete has no children, or it has one child, or it has two children. So when it has no children, basically there is no nodes under it. So for example, 18, we just simply remove it from the tree and to give this resulting tree. Next, with one child, for example, we have 25 and we have one child of 30. Since we want to delete 25, we just replace that node with the child. So we get resulting node of 20, and then we have 30 afterwards. All right. Next, we have a node that has two children. So for example, 20, we have two children, which is 18 and 30. So what we want to do here is we want to replace with the rightmost node of the left subtree. So in this example, following 18, we have to the right, we have 19, and we want to replace 19 with 20. So in the end, we will get this tree right here where 20 is swapped with 19 and 19 is gone. All right, so next we will be going into decision trees. So what decision trees are is it is a visual representation used in decision making and problem solving. So we start at the top of the tree, and based on a specific feature or attribute, we ask the question, and we follow the branch corresponding to that answer, to that question, and we reach another node until we continue this process until we reach a leaf node with a final decision or outcome. All right, so we will be talking about entropy. So entropy is a measure of uncertainty or disorder in a set of data. And here we have 10 values where 5 values are y is equals to 1, and where 5 values are when y is equals to 0. So the probability of py equals to 1 is half and py equals to 0 is half. And then using the equation, we get py equals to 0. We times it with the log of py equals to 0, and we add py equals to 1, and we times it with log of py equals to half. Py equals to 1, and then we just multiply it by a negative value, -1, and in the end we get an entropy of 1. And the highest entropy you can get is 1. So this is the highest amount of uncertainty that we can get in a set of data. All right, so now we're gonna talk about how we can calculate information gain. So it's when we take the entropy we've calculated before, which is y, and then we minus it by the weighted average of the entropy of the child node. So first we will start with the feature x1, and basically we have 6 values where x1 is equals to 1, and from there we have 3 values where y is equals to 1, and then we also have 3 values when y is equals to 0. So here we have 1, 1, and 1, and then we get the rest are zeros when x1 is equals to 1. And then using the previous equation, we multiply where px equals to 1 and y1 is equals to 1. and px equals to 1 and y1 equals to 0. And then we times it with a negative value, so we get 1. Similarly, we have x1 is equals to 0. So when x1 is equals to 0, we have 4 values, 1, 2, 3, 4. And then we get 2 values when y is equals to 1 when x1 is equals to 0. And we also have 2 values when x1 is equals to 0 and y is equals to 0. So we use the similar equation as before, and we get a value of 1. And then afterwards, we multiply it by the probability when x1 is equals to 1. So out of 10 values here, we see that there are 6 values when x1 is equals to 1, and we have 4 values when x1 is equals to 0. And then we just multiply it by the corresponding entropy that we got from here and from here. And then we just we subtract it from 1, which is the entropy we found before, and we get an information gain of 0. So this is not good because we did not get anything from this feature. So let's look at the second feature, which is when which is x2. So similarly, h1 hy is equals to 1, and then we have 5 values when x2 is equals to 1. And out of 5 of these values, we have 1 value only when y is equals to 1. And then the other 4 values is when y is equals to 0. So afterwards, we use the equation again, and then we multiply by -1, and then we get a 0.7219. And then similarly, we have x2 is equals to 0, and we can see there are 5 values when x2 is equals to 0. And out of those 5 values, we have 4 values where y is equals to 1. And then we have only 1 value where y is equals to 0 when x2 is equals to 0. And then we use the equation again, and then we get 0.7219. So from here, we get an information gain of 0.2781. When px2 is equals to 1, we see that there are 5 out of 10 values of that. And when x2 is equals to 0, we have 5 out of 10 of that. And then we just multiply it by the corresponding entropy of that. And then we subtract it from 1. And then in the end, we get 0.2781. All right, so next we will be talking about what information gain is. Basically, it is a measure used in decision trees to find the best feature to split the data on, and it helps in deciding which feature will reduce the uncertainty in the data the most. And we want to find which of these features have the highest information gain. So, and then we want to split it on that feature and then repeat it for all other attributes. So we will consider this data set, which is the tennis data set. And as you can see here, we get the highest information gain from Outlook, the feature Outlook, and then we want to split that data set based on Outlook. So for example, you can see here it is sunny, and then overcast, and then rain. And then we want out of the other 3 features here, we want to see which of these has the highest information gain. And for sunny, we get humidity that has the highest information gain, because as you can see here, when humidity is high, all the values for play tennis is no. And when humidity is normal, we can see that play tennis is all yes. And similarly for overcast, we can see that we don't have to split the data anymore, because when Outlook is overcast, all the values are yes, so it is fixed already. And similarly for rain, we can see that wind has the highest information gain, because when wind is weak, we get the values yes for play tennis. And when wind is strong, all the values are no. So we can split the data on that and get a corresponding decision tree using the ID tree algorithm. All right, next we will be talking about Bloom filters. So Bloom filter is a space-efficient data structure used to check the membership of an element in a set. So it's designed to quickly tell you whether an item is probably in the set or definitely not in the set. So we can use the hash function to insert elements to an index for storage and retrieval. So we can see an example here where the hash function is the length mod5, and we have two data, so which is edu and data. So we can see there are three values and three letters for edu, and then 3 mod5 will give us 3. So we insert a 1, 2, 3. And then we have data where the length is 4. And when we do 4 mod5, we get 4, and we insert 1 into 4. All right, so we have a question now. So which of the following is impossible for a Bloom filter retrieval? So retrieving an element that is A, B, C, or D. I'll give you about like 10 seconds just to think about this question. All right, so the answer is D, not indexed in the array and in the set. This is because if an element is not indexed in the array, so the Bloom filter will definitely not indicate that the element is in the set. So a Bloom filter can only produce false positives, so indicating that an element is probably in the set when it is not, but never false negatives. So if an element is not indexed in the array and it is guaranteed that the Bloom filter will not mistakenly claim that it is in the set. So basically, a summary of what I've said about Bloom filters is that we have to first initialize the array to all values being false, so 0. And then afterwards, we use the hash function to hash elements to an index in the array. And basically, we change it from false to true, so from 0 to 1. And then when retrieving the particular element, we check if the index is true to determine whether it is contained in the array. So if all the values that we've checked are false, then the element is confirmed that it is not in the set. While if all the elements are true, if we see that there are ones in the array, we know that it might be in the set, but it's not 100% positive that the element is in the Bloom filter. So if it's an array and in a set, it is positive. But if it's not in the set and it is in the array, then it is a false positive. While if it's not in the array and in the set, it is a false negative. So that's impossible. And while if it's not in the array and not in the set, then it is negative. All right, so I'll pass it on to Meet now. Thank you.
Yeah, guys, let me share my screen real quick. Yeah, so far we have looked at the concepts of binary search tree, decision tree, and Bloom filters. So further continuation with computer science section, we'll look at big data. What is big data? Big data basically comprises of 3 V's: volume, velocity, and variety. Volume stands for the scale of data, right? The scale of data can be in terabytes, petabytes, zettabytes of memory. Velocity corresponds to the speed of transmission of data, the speed at which your data is transmitted. For example, whether it is a real-time queue count of streaming applications. Another example is that healthcare monitoring devices, stock market data. These are all real-time data and they're pretty quick. Third type is variety. What is the type of your data? Whether it's a relational database data, whether you can store it in a database or not, whether it's a streaming data, graph data, text data, image data, audio data, all this type of data are constituted in variety. Now I want to specifically talk about streaming data because streaming data is very tricky to handle because it's changing continuously, right? What is streaming data? Streaming data is like an influx of continuous, noisy, massive, and complex data. This type of data is changing every millisecond. For example, if you want to store the log of a satellite on its trajectory, how would you store it? The trajectory of a satellite is changing every millisecond, and you have to store the log of each and every millisecond of it. So what are the methods to store continuous data? One of the method is sampling. Now, sampling uses a sliding window approach to keep the most recent elements. For example, in a batch of 100, we'll only store around 10 data points, or we'll store only around last 10 data points. So this is a sliding window approach, and it only samples a certain amount of data. So we'll still have an fault tolerance to incomplete data. So for that, we have sketching. Now sketching stores the summary of all the data points, and it's a very complex algorithm because it uses approximation algorithm and concentration inequalities. It's a complex method, but it's a bit reliable and it's better than sampling. The second thing I want to talk about is Hadoop. Now, whenever you're working on big data, there is a 99% chance that you're working with Hadoop. Hadoop is a distributed computing framework designed for processing and analyzing big data, right? It uses a MapReduce programming model. Now let's talk more about MapReduce programming model. It enables you to perform parallel computation. You could have your one task run parallelly across multiple computers. Then it's scalable to large scale data sets, it is fault tolerable, and many more. So what is mapping in MapReduce, right? What does mapping do is that it splits the data into smaller independent pieces that is processed across multiple nodes. For example, you have 100 GB of data, okay? And that 100 GB of data would be divided into 10 pieces of 10 GB each and divided into 10 different nodes. So each node would have to process around 10 GB of data. So mapping would work like that. And after that, the reduce function, the results are shuffled, aggregated, and combined efficiently to produce the output. So all these 10 nodes would shuffle and sort according to a key and aggregate all the common input into one single data point. And all these 10 data points are reduced in just 2 or 3 data points. And after that, we get the output. So let's understand it more by an example, so you guys can understand it more clearly. This is one of the example of MapReduce in action. Now, suppose think about you're a data scientist at an e-commerce company, okay? And you are tasked to analyze the revenue of each product. The data is around 100 petabytes. Now, think about this. 100 petabytes is a very big number. So how would you do it? One naive approach is to run a SQL script in the database. Just write select product category, sum revenue from table group by product category, right? That's a very naive approach, but think about it. It's 100 petabytes of data and your database would surely fail in processing this much amount of memory. So another logical approach is that you should incorporate a MapReduce programming model. And how does that work? So you have a mapping function, okay? Now this mapping function will map the product category and its revenue generated. So here product category is the key and revenue generated is the value, okay? Example map hoodies 1, 200 million. So hoodies 1 product category has produced around 200 million of revenue. Similarly, After that, it would shuffle and sort according to the key. So here, hoodies1 is the key. And for second instance, we have hatch status key. So it would sort all the keys in whatever order you have determined. And after that, the reducer function would aggregate all the similar keys into one. So example, you have reducer function of hoodies1, and you have two instances of hoodies1. So you're aggregating hoodies1 and you're getting the total output. So now you know that hoodies1 product category has produced around 450 million of output. This is just a glance at how MapReduce function works. But if you try to implement it, it's a very complex process. And the fundamentals are quite clear, but implementation is difficult. Now you have looked at the big data, right? Now let's look at graphs. What are graphs? Graphs are a very simple data structure used to represent relationship between objects through a network consisting of nodes and edges, right? There are two types of graphs, undirected and directed. This graph that you're looking at is an undirected graph because the edges have no directions, okay? And the second graph, the edges have directions. That's why it is called a directed graph. It's pretty easy, and some certain example of directed graph are website navigation page. For example, a website navigates you from home, product to whatever you want, okay? And the undirected graph, one example is social network graph. Now, how do you represent this graphs? Okay, one way to do is that through adjacency matrix. Now, adjacency matrix is a size of n cross n, where n is the number of nodes. And you create this matrix, and to input the values, we usually put 0 if the nodes are not connected, and 1 if the nodes are connected. So for example, this 0, 1, 2, 3 represents all the nodes. So 0 and 0. Is 0 connected with 0? No. So we put 0 there. Is 1 connected with 0? Yes, 1 is connected with 0. So we put 1 there. Similarly, we fill out all the values, and this is one way to represent the graph using an adjacency matrix. The second thing is an adjacency list. We similar approach in matrix, we just create a list of all the nodes and its connections. For example, node 0 is connected with 1, 2, and 3. Node 1 is connected with 0 and 2. Likewise, we create list for all the nodes in the graph. So it's very straightforward and it's very simple. Next, we will look at breadth first search and depth first search. First, we'll jump on to breadth first search. Now, what is a breadth first search? Okay. Breadth first search uses a queue data structure for finding a path. And in queue data structure, if you know the queue data structure, you would know that it uses a first in and first out approach. So let's quickly look at the path of this particular tree, how the path of this particular tree is determined using breadth first search. Now imagine you have two queues, okay? One is a temporary queue and another is a queue to store the path. Now in temporary queue, we would store the nodes that we're traversing, okay? So let's start with 0. So we have inserted 0 in our queue. So we have 0 here. And then we will look at the neighbors of 0. So it's 1 and it's 2, okay? We would add this neighbors into a temporary queue. We have 1 and 2 in our temporary queue. Now we traverse to 1 and add it to a queue. We'll traverse to 2, add it to a queue. Now we would add neighbors of 2 our temporary queue. We have 3 and 6. Just look at the directions. 2 is directed towards 6, 2 is directed over 3. We would look at the direction and add the neighbors of this particular node to a queue. Okay. So we have 3 in our queue and we have 6 in our queue. Now we would move to 3 and add it to our path finding queue. Then we would go to 6 and add 6 to a path finding queue. Look at the neighbors of 6, it's 4, add 4, go to 4, add it to the queue, and at last we have 5. So we would add 5 to the queue. So it's very easy, and it's very easy to understand how this queue data structure works. The next thing that I want to talk about is the depth first search. How does depth first search work? So the only difference between BFS and DFS is that DFS uses a stacked data structure, right? And stacked data structure, you have first in and last out approach. Okay. Now, similar to our understanding of previous example, you had 2 queues back there, and now you would have 2 stack. One stack for the neighbor traversal and another stack for the path finding. So this is our second stack. So you will start with 0. We check the neighbors of 0, 1 and 2. We add 1 and 2 our stack. So now our stack contains 2 elements, 1 and 2. Now we'll go to 1, pop 1 from our stack, add it to our another stack. Check the neighbors of 1, 2. 2 is already in our stack. Go to 2, pop 2 from the temporary stack, add it to our path finding stack. Now our temporary stack is empty. So how would you fill it? You would look at the neighbors of 2. We have 3 and 6. We would add 3 and 6 to our temporary stack. Go to 3, pop 3 from there, add it to our path finding stack. Check the neighbors of 3, which is 4. Now think about it. Our stack contains 4 and 6. Okay, but since we are using a first and last out approach, 4 is first, then 6. Okay, 4 is in a position 1 and 6 is in position 2. So we'll go to 4, pop 4 from temporary stack, check the neighbors of 4, is 5, add 5 to our temporary stack. Now our temporary stack contains 5 and 6. So we'll pop 5 from there, add it to there, and now our stack only contains 6. So we pop 6 from there and add it here. So we have 0, 1, 2, 3, 4, 5, 6 as our path. So if you think about it, the only difference is that the algorithm behind it, right? It's just first in last out approach and first in first out approach, FIFO and FILO. That's the only difference. This is TFS and BFS in action. So similar, it's just TFS uses a first in last out approach and BFS uses a first in first out approach. Now let's look at KCore. What is KCore? Okay. KCore is a subgraph of a graph where each node has at least k neighbors and where k determines the degree, right? How many nodes are that particular node connected, or how many neighbors does that particular node have? For example, node E has 2 neighbors, F and G. Okay, that's why it is a 2-core. Now, how do you determine a maximal KCore? Okay. Now, there are 4 steps involved with that. It's very easy and it's very straightforward. First of all, you determine the degree of each vertex or each node. Then, for example, if you want to find maximal 2-core, okay, you have annotated all the degrees of all the nodes, and you want to find maximal 2-core. Now, you remove the node which has less than k neighbors, okay, which have less than 2 neighbors. So in this case, F is the node which only have 1 neighbor. So we would remove that from this particular graph and update our degree. So after removing F, we would update the neighbors of A, because now it only has 2 neighbors, B and C, because we have removed F. So at last, our graph would look like A, B, C, D, G, H, E, and I only for maximal 2 cores. We would look at this particular question in further details. Now I want to hand over this stage to Faris to further continue with questions.
Yeah, I hope everyone can see the slide. All right. Thank you, Meet and Jocelyn, for the very good explanation. So let's take a look at the questions relating to computer science part. To start off, let's take a look at the questions relating to binary search trees. To start these questions, we want to identify certain valid binary search trees. So this first question asks us, is this a valid binary search tree? Let's take 5 seconds to think about it. And the answer is no. Primarily because the node A has 3 children. And we all know the binary search tree can only have at most 2 children nodes. So the properties of binary search tree will preserve entirely. Second question, is this a valid binary search tree? Let's have 5 seconds to think about it again. And the answer is no. 4 is smaller than 5. We all know that in binary search tree, all nodes to the right of a chosen node should have bigger values. The converse is also true for all the nodes on its left. So if we say the 5 is the parent node of 2 and 8, we have to say that all the nodes on the right-hand side of the node number 5 has to be bigger than the 5 itself. But we can see here that node number 4 is smaller than node number 5, and it shouldn't be on the right-hand side of the node number 5. Instead, where we're going to put the number 4 is exactly right to the left of number 5 and above number 2. And this will preserve the property of the order of values in binary search tree. Next, is this a valid binary search tree when we are dealing with a node with no children at all? Let's have a 5 seconds to think about it. And the answer is yes. As long as it has at most 2 children and the order of values is preserved, which is smaller on the left and bigger on the right, when insertion and deletion processes occur, then this is actually a valid binary search tree. How about a null pointer instead? We all know when we want to construct a binary search tree, we start off with a pointer. But if we don't have any node at all, do we still consider it as a valid binary search tree? Let's think about it for 5 seconds. And the answer is no, because it is a pointer, not a data structure. We all know that binary search tree also need to have at least a node to preserve the 2 qualities discussed in the previous questions. Let's take a look at how to remove the uppermost parent node value 7. We learned about how to insert, search, and remove certain nodes, but how about removing the uppermost parent node? In this case, the value number 7. To start off, we want to observe the children first. So we have 3 cases to observe here. We have no children, 1 child, or 2 children. Because we are dealing with node number 7, we observe that node number 7 has 2 children. So that's the option C. So what we want to do is to find the in-order successor. In other words, it's basically the number next bigger value to number 7. And we can see in this tree in particular, the next bigger value is number 8. So 8 is the in-order successor. In a more systematic way, how to find the in-order successor is by looking at the right subtree, and we take the leftmost node. So the right subtree is whole thing right here, and then the leftmost node is a node number 8. So what we want to do with it, in-order successor, is to take the node in-order successor and bring it up to the node number 7 when we remove the node number 7. So graphically, it will look like this. And we can say that by removing node number 7, if we follow the right steps, the properties or the composition of binary search tree should preserve. So the number of children and the order of values supposed to be preserved even after node number 7 is removed, and some nodes are removed in between. Next, let's take a look at questions relating to the decision trees. We know that entropy is one of the very most important things that constructs information gain for us to construct decision trees. So let's understand a bit more about entropy. What if we are given to identify members of bikini bottom, and we are given a small sample of 2 people to choose from? So person A and person B. So what is the entropy if 1, we have A, SpongeBob, and B, Patrick, and we have to choose one of them and decide whether or not they are the members of bikini bottom. Let's have about 3 seconds to think about the entropy. And the answer is the entropy is 0. But why exactly? Let's take a look at the second question, and then we think about what is entropy actually. What if we are given with SpongeBob and teammate Turner from the Fairly Odd Parents? And the answer is the entropy is 1. But what is entropy? So what has Jocelyn defined? Entropy is the degree of uncertainty or surprise involved. So in this case, when we are looking at the samples, in the first case, we know that both SpongeBob and Patrick belong in the bikini bottom. So when we are given to pick one of them, there are no surprise involved because both of them belong in the bikini bottom. But when we are picking samples consisted of SpongeBob and Timmy Turner, there are like a maximized uncertainty. There is about half likeliness in picking bikini bottom member and non-bikini bottom member. What if we change the samples? Like we have Aang, the last airbenders, and we have Timmy Turner as the second person in the sample. So it turned out that we are given with entropy as 0, primarily because there's no surprise involved because none of them belong in the bikini bottom. Next, let's take a look at Bloom filters. So the question goes, what is the impact of adding too many elements to a Bloom filter or setting the false positive rate too low? Option A reduces the memory consumption of the Bloom filter. Option B improves the accuracy of the Bloom filter in detecting element presence. C decreases the computational overhead of adding elements to the Bloom filter. And D can lead to an increased chance of false positives. Let's think about it about 5 seconds and have a go yourself. And the answer is D. Let's take a look at individual questions and figure out why all of them are wrong. So for option A, we say that adding too many elements actually increases more memory consumption. So it does not reduce the memory consumption, so option A is wrong. B, setting lower false positive rate may reduce accuracy, especially when the number of elements increases. So that is why when we add too many elements, it does not actually improve the accuracy. So option B is wrong. Option C, computational overhead may increase, especially when the filter needs to be resized. So C is wrong because it does not decrease the computational overhead of adding elements to the Bloom filter. So we're left with D, so D is the right answer, which is it leads to an increased chance of false positive when we add too many elements or setting the false positive rate too low. Second questions. Select true statements on Bloom filters. Option A, allow for efficient element removal. Option B, precisely determine false negatives. Option C, have built-in mechanism to avoid false positives. And option D, 100% accuracy guarantee in element containment. Let's have it a go for 5 seconds and think about it. And the answer is none of them. All of these statements are wrong. Let's have a look why. So for option A, we say that deleting elements actually requires to resort to more complex techniques. And we know that Bloom filters are not particularly designed for us to remove elements instead, but we can add element easily. So option A is wrong. Option B, there are no false negatives in Bloom filter. It's literally impossible as explained by Jocelyn. We say when the filter says it is absent from the system, we can say that it is guaranteed to be absent from the real set. So it will never detect false negatives. So C, we can actually control for false positives, but we cannot entirely eliminate false positives. So we can minimize the problem of false positives, but there's no built-in mechanism to avoid entirely false positives. For option D, due to hash collisions, we actually will observe false positives, and this actually compromises the accuracy. So that is why there is no 100% accuracy in element containment, because false positive is still there regardless when we can't see anything regarding to false negatives. So there is no 100% accuracy in the Bloom filters. We have to resort to more complex techniques, more systematic system to find better accuracy element containment. And the last question, let's take a look at graph KCore particularly when the question asks for us to draw maximal 3 core. So how do we go about with this? As Mead has explained, we want to label the number of edges each vertex has, or we call it as degree. And we want to remove vertices with less than 3 connections because we want to draw 3 maximal core, and then update the number of edges each vertex has, or the degree of each vertex. So from the picture previously, what we want to do is to label individual nodes with the number of edges that they have. So we call it a degree of the certain nodes. So we know that, for example, V8 has degree of 2, V7 has degree of 6 because it has 6 edges, and we do this to all the nodes in the graph. And what we want to do is to remove one by one nodes that have less than 3 connections. So we know that V12 and V5 has less than 3 connections, so we remove them. And when we remove them, what we want to do is to update the successor nodes with new degree instead. So we can see in the previous section, V6 has 5 edges or degree of 5, but now when we remove V2, V6 has 4 edges instead, and that is the updated degree. And we repeat this process recursively until we are left with one graph that is only consisted of nodes connected to 3 or more edges, 3 or more nodes, or 3 or more edges. So at the end, we are left with maximal 3 core. And that wraps up the question part for computer science. Thank you.
Okay, so thanks everyone for joining us so far. I think as of now, we'll probably take maybe a 5-minute break. Yeah, just give you like a chance to, stretch your legs, relax, that kind of thing. So thanks everyone. Will, did you want to mention something about pictures?
Yeah, so the last slide that we just passed was a picture slide. So if you guys could what's the code? Unblank the screen, sorry.
Yeah.
Show your video, yes. That would be great for us.
Yeah.
Cool. So we'll take the picture in like 5 seconds. 5, 4, 3, 2, 1. Thanks, guys. Appreciate it. And we'll be back at 12:23.
Okay, so hopefully everyone's back by now. I'll just reshare my slides and we'll go into the business section. Okay, hopefully you guys can see the slides. So we're going to get started with the final section, which is the business section or the econ section. Yeah, let's get into it. So we've already kind of touched on the types of data in terms of qualitative and quantitative, but let's also go over primary and secondary. So you've probably heard of these two before, either in high school or anywhere else. But primary data is data that's collected directly from the source by the person that wants to use it, whereas secondary data is collected by someone else. So it's collected by an individual who is not the original user. So the researcher might get their data from somewhere like the ABS website, and that's secondary because they haven't then collected it themselves. But why do we actually need effective data collection methods? So whenever we're conducting research, the whole point is that we need to be able to draw accurate conclusions from our results. So we need to maintain the integrity of our research and reduce the likelihood of error. Another, I guess, use for research in like a business sort of setting is that a company can use this data to identify their target market, and then they can reduce marketing costs by targeting that market specifically with their marketing to increase the return on investment there. Let's also go over types of data structures. So there's actually three main types. We have the cross-sectional data, we have time series, and we have the panel data set. So cross-sectional is when you measure the same variable at the same point in time, but across different individuals. Time series is also the same variable, but this time across different points in time. And panel data set is a combination of the two. So it will be across different points in time and across different individuals. A panel data set can be either balanced. So we have all data entries for all individuals in all time periods, or if we're missing some entries, then it can be unbalanced. It's probably easier to see this in a sort of more visual format. So let's have a look at these tables. So for cross-sectional data, you can see that all the variables, like all these measurements, have been taken at the same point in time, right? But they've been taken across different individuals, individuals 1, 2, and 3. But it's actually the other way around in time series, where the individual has been kept constant, and this time the measurements are taken at different points in time. If we look at the panel data set, you'll see that this is a combination of the two. So it'll look like this. So we've got individuals 1, 2, and 3, as well as timestamps 1, 2, and 3. So assuming we have all of these measurements, this table will represent a balanced panel data set because we have all individuals in all time periods. If, for example, this entry was missing, the 2-1 entry was not there, then this would mean that the data set is unbalanced because now we're missing one of the data entries for individual number 2. Moving on, let's look at data collection methods. So there's two main types of data. One is observational and one is experimental. So in observational data, essentially what happens is the researcher is not in control of the environment or the response variable, right? So the observational data is collected purely by observing a relationship between explanatory and response variables. The issues with this is that since the researcher is not actually in control of what's happening, they're simply observing, this type of data is ineffective at determining causal relationships, and it also takes a long research time. On the other hand, you have experimental data where the researcher will assign a treatment group, a treatment to a specific group. So they will assign a control group and a treatment group. They will impose the treatment on the treatment group, and then they will observe changes in the response variable. Because of the researcher's involvement, this is generally a stronger evidence than observational data, and it requires less time because it's more targeted and streamlined, but it is expensive because you need to set up those control groups and those treatment groups, impose the treatment, then record results, etc. But usually in statistics, it's very inefficient to sort of analyze a whole population of data. So if you want to think about, for example, a survey that we want data on the entire Australian population, it's probably not efficient to survey all 25 million people individually. So what we might instead do is select a sample and use the results we get from that sample to then represent the results of the entire country. But how the sample is selected is very important, as we don't want to introduce any selection bias. And selection bias is an error that can occur due to a non-random sample of the population. So when some members of the population are less likely to be included, your sample will be biased and the error in your results will be increased. So whatever conclusions you end up drawing from your research will probably turn out to be incorrect. A type of way to introduce selection bias is also by having self-selected samples. So this occurs if we're conducting the survey, when individuals are given the freedom to decide whether or not to participate. So you can think of this, for example, if a store is asking for feedback in store, then it's very unlikely that people who have an average opinion will actually opt to complete the survey. Perhaps people who have strongly positive opinions or strongly negative opinions are more likely to complete the survey, but that will just skew your data because you're not actually getting the full picture. So it's important for the sample to be selected completely randomly to avoid bias. So let's look at an example of a natural experiment. And a natural experiment is basically an empirical study in which individuals are exposed to experimental control conditions, but they are determined by nature. So this is a way to collect observational data because it's not in control of the researchers. For example, the case study is that there's a smoking ban that's imposed for 6 months in Randwick, and over 6 months, there's a 40% decrease in the rate of heart attacks. But once the ban is lifted, the rate of heart attacks increases. So remembering that this is observational data, even though it looks like we can sort of define a causal relationship between the ban and the rate of heart attacks, since the researchers are only observing changes, they don't actually have control over who gets the ban for how long or how strict of a ban certain areas get. This data cannot be used to determine a causal relationship because it is observational data. This is also a very common type of exam question where they will give you a scenario and ask you what are the problems with this experimental design. So you want to consider how your variables interact with each other and if there's any external factors which will impact the accuracy of your experiment. So this is actually straight from one of the tutes, but Jenny Craig is a weight loss intervention. Their commercials show a photo of some celebrity before and after. And question A asks, what are the control and treatment? Question B asks for any selection problems. So let's first look at A, remembering that the control group is a group that hasn't been changed, and the treatment group is the one that has been changed by the researcher. So in this case, the control group is the weight before the treatment, so there's no change, and the treatment group is the weight after joining Jenny Craig, because then we have imposed changes. And for part B, this seems pretty intuitive, but the issue here is that Jenny Craig obviously will select their best success stories to show in their advertisement. So there's clear selection bias here because they're only going to show whatever makes themselves look good. So this is not an accurate representation of the entire the entire company and all of their clients. Okay, so let's look at linear regression. So in the stats part, we would have learned linear regression. But now when we're looking at this sort of equation where we have a predictor variable X trying to predict a dependent variable Y, there's a Y-intercept, which we call beta naught, and there's a weight on the predictor variable, which we call beta 1. In the case of multiple linear regressions, there'll be multiple weights and pairs of predictor X variables. How we want to think about this coefficient beta 1 and here beta 2, beta n, etc., is that the beta coefficient is the regression parameter. It represents the causal effect of the variable X that it's the coefficient of on the dependent variable Y. So for simple linear regression, it's very simple. the change in y is proportional to the change in x, and the constant of proportionality is beta 1. For multiple linear regression, we then think of it as the change in y over the change in a specific x variable. And this notion of ceteris paribus just means we can assume this. When we assume this, we think of all other variables being kept constant. That's how we come up with this relationship. So we're only isolating one particular x variable. All right, let's look at an example question for linear regression just to see this in action. So we want to consider an experiment where a certain agency would like to see the effect of modifying a car on its market value. So they've placed all stock cars in a control group, which means Xi is 0 because there's no treatment applied. And the cars that have been treated or modified are in the treatment group. We treat them as having Xi is 1. Then the agency is trying to predict car prices, which is the Y variable or the dependent variable. So if we use ordinary least squares to estimate the parameters, and we assume all other relevant factors are kept constant, which of the following is not correct? So let's just systematically go through all of these 4 options and see which one turns out to be not correct. So for option A, we have a control group with unmodified cars, and we're trying to figure out the sample mean, right? If we substitute Xi equals 0 into this given linear equation here, and we're ignoring u because that's like the vector of other relevant variables, but we don't need to worry about it. So we substitute 0 into this equation here, that ends up getting rid of the beta 1 variable, and we're just left with beta 0. So the intercept of this regression model is the sample mean of y, because remember the intercept was beta 0. So option A is true. If we look at option B then, option B says a positive estimate for beta 1 provides evidence supporting the hypothesis that modifying a car leads to an increase in market value. So we're looking at beta 1, which is a regression parameter on Xi. And we have to remember that regression parameter means causal effect, right? So if beta 1 is positive and we increase Xi, then Y will also increase because it's a positive correlation or a positive relationship. You can also think about it as, since we're adding a positive value, obviously the output value will be higher than before. Since Y represents the market value and beta 1 being positive does support this hypothesis, that means option B is also true. So moving on to option C. Option C is about the treatment group. So now instead of Xi equals 0, we actually have Xi equals 1. So similar to option A, when we substitute it into this equation, we essentially get that Y is beta 0 plus beta 1, right? So the sample mean for the treatment group is indeed the sum of the OLS estimates of beta 0 and beta 1, because it's literally beta 0 plus beta 1. So we've come to the conclusion that option C is also true. If we read option D, you'll very quickly realize that it's a direct contradiction to option C, because it's once again about the OLS estimate. It's about the sample mean of Y for everyone in the treatment group, but we've just shown that it's actually the sum of beta 0 and beta 1, not beta 0 alone. So that means option D must be false. So after looking at all 4 options, we found that option D should be the correct answer to this question. Just 2 last things to go over. So first is confidence intervals. Confidence intervals is essentially something statisticians use to measure uncertainty in a sample variable. So we might take multiple samples when we're doing our research. And essentially, if we find the standard error of the sample mean, so for all of these samples, we find the mean, then we find the standard error using this formula. Then we can construct a confidence interval using this formula. So for example, a 95% confidence interval will, over many repeated samples, contain the true population mean 95% of the time. So why we have a plus minus here is that we're actually getting 2 values to be the endpoints of our intervals. The 1.96 here is a Z-score because it means you are within 1.96 standard deviations of the mean, which is where 95% of your observations lie. So some general notes about confidence intervals is that if you're using confidence intervals to estimate a regression coefficient, and you find that 0 is contained within the confidence interval, then there's a possibility that the variable that you're looking at actually has no effect on the variable that you're predicting. And also in general, the smaller the sample size, the wider the interval, because there will be more uncertainty. And finally, we're going to look at the difference between machine learning and econometrics, or their relationships. So machine learning is when you train an algorithm and you use it to predict a variable. So you'll have a test data set and you have a training data set, and the sample used to estimate parameters of a regression model is called the training sample. So the algorithm will use your training data set to estimate all the beta values, and all the X values in this case are called the features. The beta values are called the weights. And this will help you predict your Y variable. So in machine learning, unordered discrete choice models are called classification problems. And we also have prediction problems, which is where you actually predict the Y variable. These can be supervised, which is when there are outcomes and predictions, so it's the whole equation. Or these can be unsupervised, which is when you're sort of not really looking at predicting a variable, but just clustering the data that you already have. And essentially, the main difference you would want to know is that machine learning stresses about the accurate prediction of Y, usually. But econometrics is more focused on inferences about relationships. So you want to be able to describe what's going on. And finally, they both are ultimately acceptable approaches to data analysis. They're just both used in slightly different ways. Okay, now I'm going to pass on to Will, who'll take you through some questions.
Thanks so much, Aria, for the amazing presentation. I will be starting on the business questions. So hopefully you guys can see my screen, and we will get started right away. So the first question that I have for you guys is a bias question. In all our lectures and all the questions, it is very important to consider what sampling bias or selection bias is. So the question is, in the study investigating the factors contributing to business success, the research team decides to analyze currently active businesses. But Sarah thinks that there may be a certain amount of bias if we just sample this way. Do you agree? I will give you guys 10 to 20 seconds for this question. Pop your answers in the chat if you want to, and I'll go through it. Okay, so hopefully everyone has had a little bit of a thought about this question. So the first main thing that I like to think about is understanding what exactly are we sampling from. So we're sampling from currently active businesses. Does that create a selection bias? And in this case, yes, there is. So this type of bias is called survivorship bias. So you may have remembered from the tutes, there was a similar question about an airplane surviving and sampling from those. So in this case, survivorship bias is a subset of selection bias because we're only looking at successful businesses. Okay, so in this case, if we sample only from successful businesses, we can't tell what factors influence the unsuccessful businesses, and therefore we can't actually decide what factors contributed to successful businesses. Okay, cool, that's great. So next question. This is a question from the tute, part A, but our edu team have come up with a second question, a causal study. So this question, suppose at UNSW you want to find the relationship between weekly hours spent studying and weekly hours spent working. So question A is straight from, I think, week 4 tute. So can we create this as a causal question or a correlation question, essentially? And B, the question that I want you to focus a little bit more on to think about is, can we have this as a causal study, and how do we set a causal study up? I will give you guys 20 seconds for this question to think about both. Okay, so again, hope you guys have had a little bit of a thought for this question. So let's go into the answers. So question A, right from the tutorial, is there may be other factors that create causal events. So we can't only look at these two events, and we can only think about it in terms of a correlation. So the second part that I'm very interested in is how do we create a causal study? And if you remember from the lectures, the golden standard to creating a causal study is by using RCTs. Okay, so an RCT has three components: randomization, controlled conditions, and blinding. So what does this mean? So randomization is, again, trying to create a random assignment. So we don't care about who the person is. We're just giving it a random assignment into control and treatment. So controlled conditions is when we keep everything constant and try and change what we're trying to investigate, essentially. So blinding is another little addition onto RCTs, where we can allow single blinding where participants don't know their group, or double blinding where researchers and participants both don't know their groups. So in this case, how we can set up a RCT to create a causal study for this question is participant selection. So randomization, first of all, selecting a sample of participants from the student population and randomly giving them into two groups, treatment and control. So the next thing is we create a controlled condition, so keeping everything constant and asking the treatment group to increase their weekly hours of studying. And then in this case, we can't really create a blinding because once we place someone into the control group and the treatment group, they will know which group they are in because we're asking them to increase the amount of hours studied. So there's no blinding for this test. But for things like pills, like if you were to take a pill and we were to try and test if the pill was effective, we would either give you a dummy pill or a real pill. And in this case, we can have blinding because the contestants, the people inside the groups won't know which pill they've got. Okay? Hope that makes sense. So next question is something I found very interesting, the hedonic price model and the DID estimator. So let's get started. So the scenario is, suppose there is a neighborhood called Greenville where a new subway line is being constructed to improve transportation. So the construction of the subway completes at 2022. Okay, and we want to think and we want to investigate whether the subway line has had a causal effect on house prices. So for this question, I want you guys to think about writing out equations for the hedonic price model and a DID estimator. And can you tell me the differences and look into and explaining it for me? So I'll give you guys 20 to 30 seconds again to think about it. If you have answers, pop in the chat or questions. Cool. So again, hope you guys have had a little bit of a think of this question, and let's move on into discussing the answers. So the objective and the main differences of a hedonic price model and a DID estimator. Number one, the very essence of a hedonic price model is looking at representing the attributes of a particular thing. So at the houses, let's say, we're looking at representing and creating a linear regression using the attributes of the house. So I'll document my point here. The objective is to estimate the implicit prices of the different attributes. And our DID estimator is creating a causal control group and a treatment group. And over time, we will assume something called the parallel trend assumption. So what is the parallel trend assumption? And the trend, so this assumption is that the trend in the outcome variable for the treatment group and the control group would have a similar pattern over time in the absence of treatment or intervention being studied. So essentially, we think that the time will be an important aspect of our evaluation. So once we understand this, the main difference is that the DID estimator creates a binary variable of something, of whether you are in a treatment or control group. So looking at the equations now, the first equation, where it's just a very simple linear regression of beta coefficients, x values, and u. So x1, x2, and x3, all the x variables, are essentially the features or attributes, like I said, of a house. So in this case, we're still looking at the houses of Greenville and Controlville. So looking at these attributes, and we have u here, which is the effect of all other factors. And essentially, we want to have, if you're a bit more math savvy, the covariance of the x and the u to be 0. So there is no relationship between the predictors x and the other effects u. And then, so that is our first equation for the hedonic price model. And our second equation is the DID estimator model. So we define G as a binary variable, whether you are in Greenville and whether you're out of Greenville, so in the Controlville. And we have T, a binary variable, where the house is, the price that you're looking for is before 2022, and the house that you're looking for is after 2022. So in this case, we're looking at a panel data. We're looking at the data of houses as they change over time, and we're putting a hard line of 2022 and splitting it from there. So as you can see, the difference between the hedonic price model and a DID estimator is there is an idea of an interaction term. So as you can see in front of, after the alpha 3, there is something like a T times G. So this is an interaction term. So it's almost like an AND statement. So if T is 1 and G is 1, then it's good. If T is 1 and G is 0, it kind of is 0. So an interaction term works by incorporating both aspects of the binary variables. So if you want to add more terms, you can create more interaction terms. So essentially, the most important part of a of a DID estimator is that there is a time component. So if you were to add, let's say, another variable, whether you are near the beach or not, so like 1 or 0, if you want to introduce that into the DID estimator, you must create another interaction term between time and that variable. So cool. Let's go into the next question. Sampling. So this is very similar to one of the 2 questions as well. And I think this is something that may come up in the final exam. So the question is, researchers are evaluating the effectiveness of a new tutoring program. So they collect data on their previous scores, their socioeconomic background, and class size. So do you think it was necessary to include a previous academic performance as a control variable? So I think the question is also thinking about sampling. So they randomly sampled the students. Okay, so I think it's not mentioned here, but let's think whether if we sample the students randomly and we collect all these 3 different variables, do you think it was necessary to include them? Okay, so I'll give you guys 10 to 20 seconds for this question. If you have any questions or answers, please pop it in the chat. Okay, so the answer is it's not necessary to include all these different variables if we randomly sample, essentially. So what's going on is if we randomly sample, we don't care about all these variables, essentially. And if we try and create more variables, we aren't adding into the confoundment. We aren't trying to make it better. We aren't removing the confounding variables because the variables don't matter when we sample. So essentially, the answer says, since the tutoring program was randomly assigned to students, the treatment effects should be unbiased and there will be no confounding effects. Okay, cool. And when we release these slides later, you can have a proper read of the answers and the questions if you didn't have enough time to do so. Cool. I don't think I have any more questions. So let's move on to the last part, Q&A and review. Did anyone have any more burning questions that they wanted to ask in any of these 3 sections? Any questions, any queries for the exam? Or we have some people who have previously done DATA1001. So if you want some feedback or some advice, on this particular course, you can ask now. Doesn't seem like there's any questions. So if there's no questions, I would love to give it off to a final review of the particular slides. So in statistics, we covered Bayes' rule, set operations, probability functions, and all that. Computer science, we covered all that as well. And business, we covered that. So I believe, I guess, the most important concepts that we've covered were all here. And if you watch back and look at the recordings, it'll be a really great source of revision. Cool. So this is some final resources for previous DATA1001 workshops. So they went into a bit more of R coding, where Matt and I in the subcom team, we decided to give you a bit more a bit theoretical approach, because the exam won't be on R, it will be a written paper exam. So we felt like that would be the best approach. And there will be previous workshops in UNSW data. So I believe other workshops like our machine learning workshop that we hosted in this term previously, and even more exciting workshops to come. Cool. So before we go, I would like to just ask everyone to maybe open the cameras one more time. We realized that we didn't have the ARC logo in the previous slide. So we would just have one last photo with everyone. That's okay. So if everyone...
Will, I will say, I think looking at the screenshot again, we actually did have. Yeah.
Okay.
Did have. If you look at that again.
Okay. Cool. Right. I'll trust you on that. Cool. So yeah. So first of all, thank you so much to everyone for coming. We really appreciate you staying for all 2 hours. I know it is such a trek to wake up at 11 a.m. I mean, maybe it's just for me, but waking up so early for some people. And essentially, I'd like to take this chance to thank Matthew, my co-director, my subcoms, Aria, Jocelyn, Faris, and Meet, for their input into this particular workshop. And if you don't have any questions, I'm very happy for you guys to go about with your revision. Good luck for your exams, and hopefully see you guys at more edgy workshops and DataSoc events. Make sure to keep posted and follow DataSoc event page. Thanks, guys. Appreciate it.
Yep. Thanks, everyone.
Thank you.